Okay, think for a moment about uh, power grids with zero energy loss. Or maybe quantum computers tackling problems we can't even imagine right now.
Sounds like science fiction, almost.
Almost. But it's the promise, the potential of superconductors, materials where electricity just flows. No resistance at all.
Yeah, it's an incredible property.
But okay, here's the catch, the big hurdle. For most materials, this only happens at extremely cold temperatures. We're talking near absolute zero.
Exactly. And keeping things that cold, well, it's a massive challenge for any kind of widespread practical use. It's just not feasible most of the time.
Right, but then you have these things called cuprates.
Ah, yes, the cuprates, copper oxide materials. They're really fascinating.
Because they superconduct at much warmer temperatures, relatively speaking. What are we talking, like minus 138 Celsius?
Around there, yes. Minus 138 C, which is still, pretty chilly.
Definitely need a good coat.
Yeah. But importantly, it's nearly 100 degrees Fahrenheit above the boiling point of liquid nitrogen.
And that makes a huge difference for practical applications. Liquid nitrogen is way easier to handle than, say, liquid helium.
Oh, absolutely. It's a game changer, potentially, if we could figure out how they work at these higher temperatures.
Imagine. New materials, maybe even, dare I say it, room temperature superconductors.
That's the ultimate dream, isn't it?
It really is, and that's exactly what we're getting into today. We're looking at some really recent groundbreaking research. Comes from SLAC in Stanford.
Right, published in Physical Review Letters just recently.
And their whole goal is to get a much clearer picture, a deeper understanding of what's actually going on inside these high-temperature superconducting cuprates, what makes them tick.
And it's interesting because for decades, the go-to tool for physicists trying to understand these kinds of materials, these quantum materials, with strongly interacting electrons, well, it's been the Hubbard model.
The Hubbard model. Okay, so that was the hope.
Yeah.
That this model could explain the cuprates.
That was definitely the initial hope. It's sort of the standard theoretical framework, a mathematical recipe, if you will, meant to predict how these electrons behave.
But I sense a but coming.
Well, yeah. Applying it successfully to cuprates has been tricky. The materials themselves are incredibly complex. Their structure, the interactions.
And the Hubbard model itself isn't simple either, I gather.
Not at all. So validating it, really checking if it matches reality in these complex materials, that's been a huge challenge.
So faced with all this complexity, the researchers at SLAC tried something clever. They simplified things, went down to one dimension.
Exactly. That was a key move. Back in 2021, they did something pretty amazing. They managed to create these really well-controlled one-dimensional chains, just single lines of doped cuprate atoms.
Wow. Okay. Like a necklace of atoms.
Kind of, yeah. And then they used powerful X-rays to basically watch how particles called holons behaved. Holons are, think of them as carriers of the electrons charge.
Okay, holons carry charge. Got it. And what do they see in 1D?
This is where it gets really wild for you listening. They found the attraction between neighboring electrons in these 1D chains. It was 10 times stronger than the Hubbard model said it should be.
Whoa, hold on. 10 times?
Yeah.
Not like 10%, but 10 times?
10 times. A massive discrepancy. It wasn't just a minor adjustment needed. It strongly suggested that the Hubbard model was missing something fundamental. Some other force, some extra attraction was at play.
Okay, 10 times stronger. That completely changes the picture. So the obvious question then is, what's causing this extra pull? And, how does that connect to superconductivity?
Precisely. That finding really focused the research. The next step was to look at another fundamental property of electrons, their spin.
Right, spin. Up or down, sort of.
In simple terms, yeah. They decided to investigate particles called spinions. You can sort of visualize these as representing the electron's spin component.
Okay, so first holons for charge, now spinions for spin.
Correct. And they designed a really smart new experiment specifically to look at pairs of these spinions to see how they interact in these 1D chains.
All right, let's unpack this experiment. How do they actually probe these spinion pairs?
Well, it was a multi-stage process. First, they had to make the samples, these 1D cuprate chains, which they did at the Stanford Synchrotron Radiation Light Source, SSRL.
Okay.
Then, to actually study the spinions, they took these samples to other facilities, the Diamond Light Source in the UK, and another one at Brookhaven National Lab.
Why move them around? different capability.
Exactly. They used a technique called resonant inelastic X-ray scattering, or RIXS. It's incredibly sensitive. Think of it like shining a very specific color of X-ray light onto the material,
Okay.
and then very carefully measuring how that light scatters off. Tiny changes in the energy and direction of the scattered X-rays tell you a lot about what's happening inside, specifically about the energy and momentum of the spinions.
So you're indirectly seeing the spinions interact by watching how the X-rays bounce off.
That's a good way to put it. You analyze the scattering pattern, and it reveals the dynamics of these spinion pairs.
Okay, so they've got the data on spinion pairs. Did this data finally match the Hubbard model predictions?
Well, no, not on its own. The analysis, again, showed the standard Hubbard model just didn't quite capture the electron's behavior accurately, even in this simpler 1D system.
Still falling short.
Still falling short. However, and this is really the crucial part for you to grasp, remember that extra attractive force they found in the Holon study.
But a 10 times stronger one, yeah.
When the researchers took that extra attraction and basically added it into their Hubbard model calculations, then the theoretical predictions started to match the experimental RIXS data much, much better.
Ah, okay. So the basic Hubbard model was incomplete, but add in this extra previously unknown attraction, and suddenly the model starts working much better for the 1D case.
Exactly. It suggests that this extra force isn't just some weird artifact of the Holon measurement. It seems to be a real crucial part of the physics in these 1D cuprates, affecting both charge and spin behavior.
That's a really significant finding. It points directly at a missing piece in our standard understanding. And I imagine the researchers had some strong words about the Hubbard model's overall adequacy after this.
They did. Their conclusion was pretty direct. I think the quote is something like, "Our work has shown that the Hubbard model is inadequate to fully account for cuprate physics, even in a simple 1D system."
Even in the simplified case, it's not enough.
Right. And they continued, "If the model has already failed at the 1D level, we wouldn't expect it to hold up within the more complex 2D system where high-temperature superconductivity occurs in cuprates."
That makes perfect sense. If it can't handle the simple version, it's probably not going to explain the much harder, real-world 2D version where the actual high-temp superconductivity happens.
It's a very strong challenge to the idea that the Hubbard model, as it stands, contains all the necessary ingredients.
Okay, so the Hubbard model needs help. It's missing this key attractive force. But the massive question hangs in the air. What is this force? Where does this extra attraction come from?
That is the million-dollar question right now, or maybe billion-dollar question given the stakes. It's the major unanswered piece.
Any leading theories? Educated guesses?
There is a prominent hypothesis put forward by Thomas Devereaux, who was overseeing the theory side of this research. He suggests it might be related to interactions between the electrons and vibrations in the material's crystal lattice.
Lattice vibrations.
Yeah.
You mean the atoms themselves sort of jiggling around?
Exactly. Those vibrations are called phonons. The idea is that maybe electrons aren't attracting each other directly, but indirectly through these phonons. Like two people bouncing on a trampoline, they affect each other through the trampoline itself.
Okay, that's an interesting picture. Electrons talking to each other via these lattice wiggles, these phonons.
It's a plausible idea, and electron-phonon interactions are known to cause conventional low-temperature superconductivity. So perhaps a much stronger version is happening here.
But it's still a hypothesis at this stage.
Oh, absolutely. It needs more experiments specifically designed to test this electron-phonon coupling idea in these materials. That's the next frontier.
So let's summarize the key takeaway here for your listening.
Yeah.
The big message is the Hubbard model, this workhorse theory we've relied on, it looks like it's not the whole story for cuprates.
By itself, no.
Even in simplified one-dimensional versions of these materials, it fails to capture a crucial attractive force between electrons.
A force that seems 10 times stronger than the model predicts.
And the implication is pretty clear. If it's inadequate for 1D, it's almost certainly inadequate for the 2D systems, where the really interesting high-temperature superconductivity actually happens.
That's the logical conclusion, yes.
Yeah.
And figuring out the source of that missing attraction, whether it's phonons or something else entirely, that's now critical.
Absolutely critical. Because nailing that down could be the key to finally understanding high-temperature superconductivity.
And potentially, designing even better superconducting materials in the future, maybe pushing those temperatures even higher.
And we should stress, again, understanding this isn't just some academic exercise for physicists, right? The technological implications are enormous.
Oh, huge. We mentioned lossless power grids, quantum computing, but also things like much more powerful magnets for MRI machines, faster electronics, levitating trains. The list goes on. It touches so many areas.
So this research, by showing a crack, a limitation in this foundational Hubbard model, it really feels like a major step forward. It forces the field to look beyond.
It does. It's a classic example of experiment pushing theory. The experiments showed something unexpected, something the standard theory couldn't explain. Now the theorists have to catch up, to refine the models, or maybe even develop entirely new ones.
It's like we've been using a map, the Hubbard model map, and these experiments have just shown there's a whole mountain range missing from it.
That's a great analogy. And now we need to figure out what that mountain range is made of.
Right. So this leaves us, and you, with a really provocative thought to chew on. If the Hubbard model, which has been our main guide for understanding these complex quantum materials, isn't giving us the full picture, what else could be going on down there at the quantum level?
What other fundamental forces or interactions might be at play that we haven't fully appreciated or incorporated into our models yet?
Exactly. And could figuring that out lead to completely unexpected discoveries, not just for superconductors, but maybe in other weird quantum materials or even fundamental physics more broadly?
It really opens up the possibility space. When your main theoretical tool shows its limits, it's often a sign that something genuinely new and exciting is waiting to be discovered just beyond what we currently understand. Makes you reconsider the foundations.